Hello everyone, welcome to another lecture of robotics and automation. Uh, in this lecture we shall study about coordinate transformations, and in today's lecture we are going to cover these topics. We shall start with rotating a vector, in which we study how we can rotate a vector and what matrices we require for these kind of rotations. And then we shall talk about the rotating a coordinate frame, and there also we need a rotation matrix. So we shall see some examples at how we can do that. And after that we shall talk about the vector transformations. So in this area we will talk about rotation and translation. And then we shall emphasize on the need of transformation matrices with an example of 2R planar robotic arm. After that we shall talk about homogeneous transforms, which is again a transformation matrix with some additional rows and columns. So this area till here we shall cover about 2D rotations and transformations. After that we shall also study about 3D rotations and 3D transformations. So beside this lecture, if you want further reading, I shall suggest you the book. Number 1 is the Element of Robotics, and chapter is 16. So here you shall find theory about basic transformations. The second book is the Introduction to Robotics, and chapter is 2. So these two books and these two chapters you can further use to study about these topics in detail. And also there are a lot of examples which I cannot cover in this lecture, but if you are interested you can solve more examples and problems from these two chapters. Okay, so let's begin with first of all, let's start with our robotic 2D planar robotic arm, which is like this here. Here we have a revolute joint, and then we have a link. Again here we have a revolute joint, and this is the second link, and here we have the gripper. So as you can see that most of the time what we are interested in finding the position of this end effector. Position and orientation of the and effector. So we are interested where this end effector is located. Okay, because we have to pick and place some objects. So for that, it's necessary that the exact orientation and position of this end effector is known. So how can we know this, the position and orientation? So the process of finding the position and orientation, we call it kinematics. So we can use kinematics to find the position and orientation. For that, we must first theta, the angles of these two joints, they must be given, and also the link length must be given. So if these quantities are given, then we can find the position and orientation of this end effector. So this is the motivation behind the why we are doing all this. We are studying the coordinate transformations, where we shall study transformation matrices, and the reason for doing all this is because we are interested in finding the position and orientation, and for that we need some kind of transformation of the coordinates so that we know that where this end effector is located in the with respect to the base of this robot. Okay, so that's why we want to study it. Okay, let's just revise some basic concepts. And the basic concept is, one of them is a coordinate system or coordinate frame. So what is a coordinate frame? So in a 2D or a planar frame, we have two lines that are perpendicular to each other. Let's say this is XA, YA, and the frame, we call this frame A. And here we have, at this point, we have its 0, 0 coordinates. So this is a planar or a 2D coordinate system. And then we can have also a 3D frame, which will look like all three lines, they are orthogonal to each other. So we have XA, then we have YA, and we have ZA. Okay, let's call this frame as frame B. So this is an example of a 3D frame in which we have three axes, x-axis, y-axis, and z-axis, and we call this frame B. So mostly we shall use a 2D or a planar frame in our calculations because it's easier to compute different quantities. But in 3D frame is a real world frame. Okay, in the real world everything is 3D. Our space is 3D. The robotic arms they work in 3D. Objects, they are also 3D. Even the task space, workspace, in actual they are 3D, but they can also be represented sometimes by a 2D planar frame. So yeah, So now let's define what is a position in a coordinate system. So let's say we have a coordinate frame here, a 2D one. Because of simplicity, we shall use this frame. The frame, we call it A, and in this frame we have a point P here. So in this 2D plane we have a point P, and how we can describe its position, of course we shall see that how much length is about x-axis, and also we call this length as P of x, and then we shall see how much length is along y-axis, and we call this length as Py. So now we are able to define the position of this frame, so this point P in frame A. Okay, how can we do that? Can be defined as, so we shall use P and then A. We shall write something like this, Px and Py. Okay, so this is how we define the position of a 2D point, or a point in a 2D frame, using a vector. Of course, if we are using a 3D frame, then we have to use something like this. We define like this 3D coordinate system. X, let's say this point is this frame is B, XB, YB, and ZB. And here we have a point P in this. So we shall see here what are the projections on the corresponding axis, what projection it makes on the corresponding axis, and then we can say that okay, this was a point P, and this is Px, this is Py, and this is Pz. So position of point P can be defined in 3D frame as, so we shall use P of A, P of B. Keep in mind that the frame name comes here at this position. So P is the point and B is the frame, and then you have to define Px, Py, and Pz. So this is how we write the position of a point in a coordinate system. So this was a position, and now let's talk about, so let us see how we can define orientation of a rigid body. Of a rigid body in frame. So let us assume a 2D frame with x coordinate and y coordinate, and name this frame as frame A. Here we have a rigid body, call it like this. So what we want to do, we want to define the orientation of this rigid body in frame A. So one method is we have to define here a body fixed frame, where we can say that okay, this is a body fixed frame here, and let's name this frame as frame B. It is YB and XB, and B is the frame. So to define the orientation of this body, rigid body, we have to measure the angle that it makes with the x-axis. So this angle theta is the orientation of this rigid body with respect to your frame A. Or you can say that the angle between the frame B and frame A is the orientation of the rigid body. So that's how we define the orientation in 2D. And position is simply the projection of the point on the relevant coordinate. So this is how we define the position and orientation. So here the orientation can be defined using theta. Okay, if this is now clear, then what we need to do is to now talk about the rotating a vector. So let's see how we can rotate a vector. So let me quickly draw this coordinate frame, x coordinate, y coordinate, and then we have a vector here. Let's draw this vector with line. Angle theta, orientation is theta, and so this is a vector. So if we rotate this vector, after rotation, it will look like something like this. So again, the frame is same as the previous one. So let's say it was X. So this is the X frame, and the frame remains same. We have X and Y, but this time the vector itself is rotated, and now it is like this. So what has changed? The X and Y coordinates. For example, previously, if this was the Y coordinate and this was the X coordinate, let's name them capital X and capital Y. So this was X, this was Y, and the coordinates were like capital X and capital Y, sorry, small x and small y. So after rotation, what we have now, we have an angle of theta plus phi, because this vector r is rotated by angle phi. And now we have also the y component. It doesn't look good, so let's make it a little bit more clear. So here the angle is theta plus phi, and now this is the new y coordinate, we name it y dash, and this is new x coordinate, we name it x dash, and let's make them capital to avoid any confusion. Okay, so what we did, we took a vector r and then we rotated it with an angle phi, and we get this new vector, new rotated vector with the new coordinates x dash and y dash. So how can we calculate the new coordinates? So let's see how we can calculate. To calculate the new coordinates, x dash and y dash, so what we have to do, we have to just write it like this, because we know that using trigonometry, we know that so we have a triangle here. You can see that this is our triangle, this is a right angle triangle, and we can write it like this using, we can write it that x dash or x bar is equal to r cosine theta plus phi. You can write it like this, and this can be further written as r cosine theta cosine phi minus r sine theta sine phi. So what we do, we can also rewrite it like this: r cosine theta cosine phi minus r sine theta sine phi. Now if you notice that this r cosine theta, we can calculate the value from here. R cosine of theta, using this right angle triangle, we know that this is equal to actually x component of this, which is the base. So here we have the 90-degree angle, and this is the base. This is perpendicular, this is hypotenuse. So we know that this base component, x component, will be equal to r into cosine of theta. So we can write here x instead of r cosine theta, x cosine phi minus, and similarly for r sine theta, we can write down the value of y here. So r sine theta is y sine phi, and this is x dash. So we have calculated the x coordinate, the new x coordinate after rotation. So what we need the previous coordinates before rotation, and both the x and y coordinates, and also we need the angle by which the vector is being rotated. Okay, so I think here we should write down also So this is, let's say this is figure 2. This is figure 1. And here we can write that to calculate the new coordinates x dash and y dash, consider the right angle triangle of figure 2. So by using this we can get this equation, and we get following relation. Okay, this is from the figure 2. Again we consider the figure 2, but this time for the y coordinate. We get following relation. So what is the relation? The relation is that if we want to calculate the y bar, y dash, so it will be equal to sine of theta plus phi into r. So we can write it like y dash is equal to r sine theta plus phi, which can be written as r sine theta cosine phi plus r cosine phi sine phi. Okay, here we have theta, not phi. So we can write it down, r cos theta sine phi. Okay, this can be rewritten as r sine theta cosine phi plus r cosine theta and sine phi. R sine theta, from the figure it's clear that r sine theta is equal to y component of r. So we can write it down like here, this is y and this is cosine of phi plus r cosine theta, this is equal to x component in this right angle triangle, so we can write it down x sine of phi. So finally we can rearrange it, and we can write down like y dash is equal to x sine phi plus y cosine phi. So now we have found the new coordinates, the y bar and x bar, or you can say y dash and x dash, using the previous coordinates. If we know the previous coordinates before rotation of this vector r, so what we need the previous coordinates and the angle, previous angle, and the angle by which it is being rotated, which is phi. So we can calculate the new coordinates. The above, let's name these equations as, let's call this one as equation 1, and let's name this one equation 2. So now we can write down like equation 1 and 2 can be written as matrix form. So how we can write down? We can write down like this. Cosine of phi minus sine phi, sine phi, cosine of phi multiplied by x and y. So if you multiply these two matrices, we get again our new coordinates. So where this comes from, this matrix? From these two equations here, y1 and this equation 1 and equation 2. Okay, so this matrix here, we can call it rotation matrix. We can represent it using R. So this rotation matrix, it can be used for if the coordinate is rotated or if the vector is rotated. So we can multiply this rotation matrix with the old xy components to get the new xy coordinates. Okay, so if this is clear that how we can rotate the vectors using the rotation matrix. So now let's see how we can rotate the coordinate frame. So previously we did that. Here we have a frame and we rotated the vector, and now the vector in the next example or in the next topic, the vector will remain same, but we shall try to rotate the coordinate frame, this xy axis, and let's see how we can do that. So let's say we have a coordinate frame and previously it looks like this. This black color. So we have an x component here, the y component here, and what happened? So we did some rotation, and we did rotation like this. So now this coordinate frame is rotated by 45 degree, or you can say an angle theta. So now this is the new x coordinate, which we call x bar, x dash, y dash, and yeah, so this one is the new rotated frame. So if we draw the projection of this, our new coordinate, which is the new coordinate frame, and the new x component of the this coordinate frame, which is x prime, it can be further split down to the x and y components. For example, this one, if we see the projection of the new x coordinate in the old coordinate system, which is xy, so it will be, this component will be sine theta, and this component will be your cosine theta. So let's make a projection on this axis also, y-axis, and this will be cosine of theta. So we have now successfully resolved the new coordinate x prime into its x and y components with respect to the previous old coordinates. And similarly we shall do it for the y component also. If we make a projection on the x-axis, it will be like on the negative side cosine theta, so the x component will be negative and the y component will be positive. X component will be minus sine theta, and this is our new coordinate, and y component will be cosine of theta, and yeah, so we have resolved the new x prime and y prime into the x and y components with respect to the old coordinate system. So let's say the frame is rotated by angle theta. So okay, one thing is that these x, y and x prime and y prime, they are the unit vectors along the x and y axis. So I can extend the axis like this, and same for the new rotated axis. Let's make the line so it is distinguishable from the so this is to show that these are the unit vectors along the x and y coordinates. So so now if we want to write the coordinates of these new rotated frame, so how can we write that? We have a tool that we have developed already in the previous slide, and this tool says that if you want to find the coordinates of a rotated vector, so let's see here, this vector x prime is rotated by angle theta from the original position. So we have already discussed it here that once the vector is rotated by an angle theta, okay, so here the rotation was with angle of phi, okay, but here in the next slide we have a rotation with angle of theta. So if it is rotated with angle of theta, then we can find the coordinates, the new coordinates x prime and y prime, using just multiplying them with the rotation matrix R and the original coordinates xy. So we can repeat same thing here, and we can write it down like this: x prime is equal to, it was cosine theta minus sine theta, sine theta, cosine theta, and then we have here 1, 0. 1 is because it is a unit vector here, and if you see that the y component of this unit vector x, this will be 0 because this is purely an x on the x coordinate. So that is why okay, so this this is here, you can say this is x, actually this is the x, and after multiplication you will get cosine theta and sine theta. So if you want to find the x component of the new coordinate, the unit vector, you just have to multiply the rotation matrix R with the x component of the original unit vector along x-axis. When you multiply both, you will get this one here. And similarly, to find the y prime, the unit vector along y-axis, what we need to do, we have to multiply it with the, this is again rotated by angle theta, and you have to multiply it with the original unit vector along y-axis with the, and you have to multiply it with the rotation matrix R. So let's see how we can do that. Cosine theta minus sine theta and sine theta cosine of theta. And for this time, for y, we have here this unit vector y. It has along y-axis, it is a unit vector and its value is 1, and along x-axis it has 0 value. So we can write it down like this: 0, 1, and this will be equal to minus sine theta and cosine of theta. So this is shown here. You see that the rotated frame x prime is composed of x component and y component. The x component is here cosine theta, and the y component is sine theta, which we have already calculated. And similarly, for the new rotated unit vector y prime is equal to minus sine theta and cosine of theta. Minus sine theta and cosine of theta. So this is how we can find the coordinates of the rotated frame if the rotation is by angle theta. Okay, so the purpose of doing this, we are doing it for, actually what we are interested in, we are interested in finding the position position of a vector in the rotated frame. So let's say we have a frame, and let's name this frame frame B, and in this frame we have a vector, and this vector is, let's call it P. Point is P, and the vector, let's call it R. The vector is R and it's pointing toward the point P here, and the y component will be YB, and we have the x component, let's call it XB. Now this frame is, let's say, rotated by angle theta. Let's draw here again after rotation. So it looks like this. So this is your original frame, and the frame is rotated by angle theta here. So this angle here is theta, and yeah, so now what we are interested in, so this black color is the frame B, which is the original frame, and this green color, let's call it frame A. Okay, and still we have our vector, which is, now we have to find the position in the rotated frame, the new frame, which is a B frame. So how we can do that, how we can find the position of this vector in the new frame, which is frame A. So if you see the y component of this vector, this was in the original frame, and now this is in the rotated frame, which is YB. This was YA. So this was frame B, the black color one. This was frame B, and the green color was frame A. So this will be YA, and this other one will be YB, and similarly this will be XB, and this will be XA. So that the frame A is rotated by frame B with the angle theta. Okay, now to calculate the new coordinates of the point P in the frame A. So what we need here, we need a rotation matrix where theta is the angle of rotation of the frame, and we multiply it with the original frame without rotation. So this is how you will get the coordinates of the point in the frame A. So let's see with example. Let's say the point P it has coordinates equal to under root 3 by 2 and 1 by 2. So the coordinates of the point P in the frame B are under root 3 by 2 and 1 by 2, the x and y coordinates. And the length of the vector, should we describe it as point P? That P is a point in frame B and its coordinates are these. The length of the vector r is equal to 1. So from the figure you can see here the r, this length is equal to 1. So this is a unit vector here. Okay. Now the frame A is obtained after rotating the frame B by theta is equal to 30 degree, like same we did here. So we rotated the frame B and we get a new frame which is a frame A, and it is 30 degree, the angle is 30 degree. So now what we have to do, it says that find the coordinates of point P in frame A. So the simple is that we can write down PA is equal to, we have a rotation matrix in which you can write it like this: cosine of 30 degree, then you have sine of 30 degree, and minus sine and cosine. Okay, and when you multiply it with the position vector, which is under root 3 by 2 and 1 by 2, then you will get this answer, 1 by 2 and under root 3 by 2. So this will be the new coordinates of the point P in frame A. Now let us consider that the frame is again rotated by an angle of 30 degree. And so what will be the how we can calculate the new coordinates? So imagine, consider, so this was the rotation matrix R. So if there is one more rotation, so it will be then you have to multiply one more here. You have to do one more time. You have to multiply this PA with R one more time. Okay, so your equation will look like this. And you have to multiply it with the PA, which is equal to 1 over 2 under root 3 by 2. Okay, and this will be equal to 0, 1. So it means that we can have as many rotations as we want. We just need to multiply the rotation matrix, and we have to consider how much angle that the new frame is rotated with respect to the previous frame. And these are you can say these were the coordinates of the point in the previous frame, and this is the new frame PA1. So this is how we can calculate the coordinates. Now let us see that how we can now rotate and translate frames. Okay, so we have an example of a 2R planar robot in which we have, so it looks like something. So we have a link here, and then joint, and then again a link, and then here we have a gripper or end effector. So what we are here interested is that we want to find the position of this end effector. So that's what we are interested in. We want to know the position of this end effector in your reference frame, which is, let's say, a frame A, which is a fixed frame here. So we want that the position of this end effector in this frame A. So we can attach here a body fixed frame here like this. Let's call it frame C, and then we can attach here one more frame. Let's call it frame B. So now you see that some frames are rotated with respect to our base frame. For example, frame C is rotated with respect to frame A with some angle theta, and same is true for frame B. And also they are rotated and translated. Translated means their origins are at a distance from frame A. Okay, so that's why we are studying these transformations, because we are interested in finding the transformations that if we know the position of this end effector with respect to frame B. Okay, so how can we transform this in our reference frame, which is a frame A? How we can do that? So that's why we are now studying the transformations and rotations. So let's see. Okay, so here we have frame A. Let's draw it with black color. So we have a frame A here, and then we have a frame So then we have a frame B, which is rotated and translated from frame A here. And then we have frame C, which is again rotated and translated with respect to frame B. So if you want to find out their angles, so this is the distance between the translation between frame A and frame B, and this is the translation between frame B and C, and the angle of rotation can be also calculated by which they are translated and by which they are rotated. So what we can do, we can try to develop a new tool by which we can also incorporate the include the translations along with rotations, because in the previous slide we were discussing about only about the rotations of frame 1 with respect to frame 2, but now we shall also consider the translation also. So okay, so let's begin. To find the coordinates, intermediate frame C. Okay, to simplify the things, what we can do, we can take a point. Take a point here. Let's redraw it. So what we can do, we can here like write down it like this. To simplify, consider a point on gripper. So what we do, we take a point. Let's say we say a point is P, and which is, let's say, on the origin of this point C. So the reason is to reduce the frames. So what we want to do, we want to reduce the calculations, and instead of taking the whole frame C, we just take the this origin of frame C and say we have a point here P. Okay, let's write down here a point P. So now we don't need this frame C, so we are only interested in the position of this point P in this frame B, and finally eventually in frame A. So let's draw again this frame diagram, and here what we can do, we have a frame A here. This is frame A, and then we have frame B, which is rotated and also translated. This is frame B we have here. So now we have two frames, and let's say the origin of frame C, this point P, we take it here. We say, okay, this is a point P. So it comes from here, this point. So what we did, we just ignored the frame C, and it simplified our calculations. Otherwise we have to take one more frame and things will get more complex. So now the position vector from point P in frame A is this green line, and the position of point P in frame B is this line here. Okay, and let's say this angle is phi. And I think let's take point P a little bit here, so that it's easier to draw. Okay, so this is point P we have here, and This is the position vector in frame A. This is the position vector in frame B. Okay, I cannot drag it actually. Normally it's not like this. Yes, this looks much better. So yeah, so we have here so this angle, we call it this angle as phi. Okay, and first draw the y component. Then now we can draw the angles. So this angle is phi. So the point P, the orientation in this frame B, is described by the angle phi. And in frame A, this is a position vector which describes the position of point P in frame A. So now what we are interested in, finding the position of this point in frame A. So how can we do that? We start with frame B and then we transform using the transformation matrix, the rotation matrix, and then we transform to frame A. Till now we have studied only rotation matrix, and so what we can do, we know that it is clear that frame B is rotated with respect to frame A. It is clear, and you know that if you want to find the coordinates of a new frame, okay, so what you have to do, you have to use rotation matrix. Okay, so let's draw a temporary frame here which is parallel to frame A, so we can see that how much it is rotated. Or let's make it with blue color, sorry, the black color. So here we have the original A frame if it's not translated, if both frames were at the same origin, so then it will look like this. The angle that is being made is theta. So frame B is rotated with respect to frame A by angle theta. We call this new frame, we call it intermediate frame. Let's call it frame I. This is an intermediate frame we have. So now for how we will do the conversion, we know the we know that frame B is rotated with respect to frame I. Okay, first we need to convert the frame B into frame I, and then we convert the frame I into frame A. So this is how we shall carry out the transformation. Okay, from here we can now write, to find the coordinates of intermediate frame I. So this is how we can do that. We can say that position of C is equal to position of I is equal to, we have a rotation matrix which is cosine theta minus sine theta, and then we have sine theta and again cosine of theta, and we multiply it with the coordinates of frame B. Did we define these coordinates here? XB and YB? No, we didn't. So let's define here. So in the frame B, the point P has a projection this. This is YB, and this length is XB. So we know the X, Y components in the frame B. So all we want is to find the components in the frame I. In the frame, let's say in the frame I, we have components which we call Xi and Yi. In this rotated frame, okay, so this length from here to here, this is Xi, this is Yi, and from here to here, this is Xi. This length from here to here, and from here to here, this is Yi. So we are interested in these XY coordinates. So what, as we are doing previously, just multiply it with the rotation matrix and we will get the coordinates. So now we have the coordinates in our intermediate frame. Okay, now we know that this frame is translated by a distance, by a specific distance which is delta x and delta y with respect to the origin of frame A. So here frame B, actually it is at the distance of just write down here. So this is delta. So this this distance, height, is delta y, and this length from here to here, this is delta x. So we know that the origin of frame A, it is at the distance at this distance delta x and delta y from the origin of frame B. So this frame, sorry, yes, frame B and also frame I. So it means that both these frames, frame B and frame I, are translated with respect to frame A. Okay, so that's what we did already. We have already rotated the frame, okay, into this intermediate frame. Now we have the coordinates in the intermediate frame, the coordinates of point P in this intermediate frame, frame I. And now just what we have to do, we have to do a transformation so that describes the relation between frame I and frame A. So let's see how we can do that. To get the coordinates in the reference frame A, we have to use translation, and this is how we can use it. We can say position of point P in frame A is equal to XA, YA, and what you can do, you have already XI and YI. This you have already calculated here using rotation. Now using these coordinates, you just have to add the length delta X and delta Y. So when you add these, you already know this del Xi and Yi, okay, and when you add delta X and Yx with them, you get this whole length of this vector AP. So this green vector AP, you will get the length, and this vector is in frame A, which is a reference frame. So that's how this is called translation. Okay, this is called transformation because it involves translation and rotation. Transformation is equal to rotation plus translation. So here we are doing both. Okay, if this is clear, then what we do, we move forward and let's see what are the homogeneous transforms. So homogeneous transforms, they are also transformation matrices actually, and transformation matrices are used for rotation and translation of frames. Using a single matrix. So this is how it looks like. So normally what we have, a two-dimensional vector. Okay, it looks like something like this. Let's say PA is equal to XY. So this is a normal vector, but a homogeneous for homogeneous translation, this is generally, you can say this is a 2D vector, but a homogeneous translation matrix will look like something like this. Okay, before translation vector, to make the above vector homogeneous, just add 1 below. So that's how we do that. If we want to make it homogeneous, you have to write it like this: x, y, and then just add 1 here. Okay, so this is how you add the how you make a homogeneous this vector. So the advantage of using this 1 below the xy coordinates is that it makes the calculation easier, and also it makes them also the metric multiplication also possible. But as said, it's you can write like this or also like this. It's not really, it doesn't really matter. But if you write like this, it's more like the multiplication of the matrices. Later you will see that when you have to multiply the matrices, so it becomes easier, and also the matrix look like more like symmetric matrix. So yeah, so let's see how a homogeneous translation matrix looks like. It looks like something like this. We have 1 0 0 0 1 0 and delta x, delta y, and 1. Okay, so this is a translation matrix, homogeneous transformation matrix. And if you want to see how a homogeneous rotation matrix it looks like something like this. So this was a normal rotation matrix, if you remember. So what we do here, we add 0 0 and 1 more here, column. So now this becomes a homogeneous rotation matrix, and of course this is 2D, in 2D. So this is a 2D homogeneous rotation matrix. But if you remember, this is actually the rotation matrix, all we were doing here. Okay, but to make it homogeneous, just add 1 row and 1 column, and this entity should be here 1. So that's how you do the how you make the matrices homogeneous. Okay, now we have to combine them in one matrix, one homogeneous matrix. Okay, so here what we said that are used for rotation and translation of frames using a single matrix. I think this statement is a little bit misleading. Here it can be or, Okay, now it's correct. So this is homogeneous translation matrix, and this is the homogeneous rotation matrix. And yeah, now the question is, how we can use these, how we can combine these two, rotation and translation, into a single matrix. So let's see how we can do that. I think here we have some space, so let's draw it here. Better make a new slide. Okay, so let's take again an example of that we solved previously without using homogeneous frames. And let's take this example again, where we have a frame. Should we copy paste it? I think it's better if we copy paste it, otherwise we have to draw it totally again. Let's see, is it possible to copy paste it here? Yes. So we have a point here. We are interested in finding the position of point P in frame A. In other words, we want to find the AP vector. So that's what we did already. We wanted to find the position of point P in frame A, and we had a frame B that is rotated with respect to A. So let's write down here. Frame A is a reference frame. Now frame B is rotated by theta with respect to frame A. Okay, so yeah, so frame B is rotated and also translated. Frame B is frame B is also translated. Yeah. is also translated with respect to frame A by delta x and delta y. So the origin of two frames, they are translated, they have a delta y and delta x distance between them. So what we did in the next step, so draw an intermediate frame I, that has same origin as frame B, but it is not rotated with respect to frame A. So that's what we did already here. We made an intermediate frame by ourselves. This actually doesn't exist. Okay, we draw it by ourselves. So okay, so that's what we did here. We draw intermediate frame, and yeah, so now we already in the previous slides we have calculated the position. So using rotation, first it was rotation and then we did the translation. Now we do it using homogeneous transforms. Okay, so the first was there was a rotation. Okay, previous page. Okay, continued. Okay, so first there was a rotation to find the position of point P in frame A. We need to find the position of point P in frame I, and as the two frames rotated by an angle of theta. Was it theta? What was angle between them? Yes, so the two frames, the I frame and the frame B, they are rotated by an angle theta. So let's mention here this is the frame I. Also in the previous diagrams also here we have to write this is frame I. Theta. So we use rotation matrix. So to find the coordinates in your homogeneous coordinates in your iframe, x, y, and 1. So previously we only use x, y. So now we shall use 1. To find homogeneous coordinates. So x, y, and 1. So these are the homogeneous coordinates, and then we have a homogeneous rotation matrix. Cosine theta minus sine theta, sine theta, cosine theta, 0, 0, 0, 0, 1. We multiply it with the homogeneous coordinates of the frame B. Just add 1 below. So this is how you can do the homogeneous rotation. So this whole process is the homogeneous rotations. And similarly, we can do for homogeneous transformation. So what we can do, we can have a homogeneous vector, a homogeneous coordinate vector, and then we have a homogeneous translation matrix. 1, 0, 0, 1, 0, 0, delta x, delta y, 1, xi. So we already did the rotation, and now we have to do translation. Yi and 1. So now we are doing the transformation. Sorry, not transformation, it's translation. So you just have to multiply this matrix with your coordinates of the frame I, homogeneous coordinates of the frame I, and you will get the coordinates, homogeneous coordinates of the point P in frame A. You just have to ignore the 1, and then these two will be your homogeneous coordinates. You notice that using homogeneous translation matrix, it's easier to multiply. Otherwise you have to do additions. Okay, but for using this matrix, you get a 3 by 3 and also 3 by 3. So yeah, so it's one of the advantages that you can also make calculations simpler, and also it avoids the problem of multiplication order. Okay, sometimes the matrices are not compatible to multiply. Okay, so if this is clear, now we shall see how we can perform these two operations in a single matrix. Okay. To perform rotation and translation in a single or with a single so what you can do, you can write something, homogeneous coordinates 1, and then you can write the translation 1 0 0 1 delta x delta y 0 0 1, and then you can write the rotation matrix, which is cosine theta sine theta 0 minus sine theta cosine theta 0 and then 0 0 1. So this is your rotation matrix, and then you have to multiply it with just your coordinates of frame B. So in this case, actually what we are trying to do, we are trying to get a single matrix that can be used for both of these operations. So it will look something like this: cosine theta minus sine theta cosine theta 0 0, and here we have delta x delta y and 1. Okay, so this matrix here, this we call it as transformation matrix. Of course, homogeneous, yeah, homogeneous. Yeah, so what you need to do, you need the coordinates of a point P in a frame, and then you can multiply it with this transformation matrix, and it will automatically convert the coordinates into your reference frame. That's what we wanted actually. So if you remember, that's what we wanted actually. We wanted we knew the coordinates of point P in your B frame, and we wanted in frame A, and you have to just multiply it with the transformation matrix, homogeneous transformation matrix, and you will get the coordinates in your frame A. Okay, I think the lecture time is over now, so we shall just stop it here. Yes, so that's what we were looking for, and keep in mind that this matrix is in 2D, two-dimensional. So this matrix is actually a two-dimensional matrix, and because you can see that the coordinates x, y, only we have two coordinates here. So in the next lecture we shall talk about also the 3D transformation matrices, homogeneous transformation matrices. And yeah, so we shall end our lecture here. Thank you very much. If you have any questions, just contact me by email, and you can also approach me on Zoom. And yeah, we can see that how we can solve your how we can answer your questions. Then goodbye.